Tonight, we're going to follow a spacecraft that has already left the solar system. Voyager 2. It crossed the boundary of our solar system years ago, and it is still moving, right now, through the cold emptiness between the stars. It has no engine running, no destination, no way to slow down or turn back. And almost nobody ever stops to ask the most obvious question about it. Where does it actually end up? It will keep moving when the sun is gone. It will keep moving through the deaths of the last stars. And it will still be moving in 10 trillion years through a universe that looks nothing like the one it left. By the end of tonight, you're going to understand what 10 trillion years actually looks like for Voyager 2, what the galaxy becomes over that time, and what it means that something we built is going to outlast everything we know. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Voyager 2 was launched on August 20th, 1977, 16 days before its twin, Voyager 1. It left Earth on a trajectory deliberately designed to take advantage of a rare alignment of the outer planets. Jupiter, Saturn, Uranus, and Neptune were arranged in a configuration that only occurs once every 176 years. By threading a careful path through their gravitational fields, Voyager 2 could use each planet as a slingshot, picking up speed with every close approach, ultimately reaching the outer solar system without needing enormous amounts of additional fuel. This technique is called a gravity assist. You might also hear it called a gravitational slingshot. The spacecraft borrows a tiny fraction of a planet's orbital momentum around the Sun. The planet, being incomparably more massive than the spacecraft, loses so little energy in return that the effect on its orbit is essentially unmeasurable. But for the spacecraft, the gain is significant. Every planet encounter was a free boost from orbital mechanics, planned years in advance, executed with extraordinary precision by teams of engineers and scientists who had never done anything quite like it before. The entire mission was possible because of a graduate student named Gary Flandreau, who, in 1965, was working at NASA's Jet Propulsion Laboratory and noticed that the outer planets would align in the late 1970s in a way that hadn't occurred since. Thomas Jefferson was president. He calculated that a spacecraft launched at exactly the right time could visit all 4 outer planets using gravity assists from each one. His work launched a mission that would define interplanetary exploration for the next half-century. Voyager 2 swept past Jupiter in July 1979. The instruments returned images of the Great Red Spot in unprecedented detail, showing it as a vast, counterclockwise rotating storm system large enough to swallow multiple Earths. They observed active volcanic eruptions on Io, the innermost of Jupiter's 4 large moons. This was the first time active volcanism had ever been detected on a body other than Earth. Io is the most volcanically active place in the solar system, driven by the intense gravitational kneading it receives from Jupiter's immense gravity and the other large moons. The spacecraft also captured images of Europa, a world covered in ice with a subsurface ocean that planetary scientists now consider one of the most promising places in the solar system to search for microbial life. Then the spacecraft curved around Jupiter's gravitational field, picking up speed, and continued outward towards Saturn. It swung around Saturn in August 1981, studying the ring system in extraordinary detail and examining the moons, including Titan, with its thick nitrogen atmosphere, the only moon in the solar system with a substantial atmosphere. Titan's surface was hidden beneath an opaque orange haze, its secrets not fully revealed until the Cassini-Huygens mission decades later. Voyager 2's Saturn encounter gave it the gravity boost needed to reach Uranus, something no spacecraft had ever attempted. It flew past Uranus in January 1986, becoming the only spacecraft in history to visit the ice giant and its system of moons and rings. Uranus is a strange world, tilted almost completely on its side. Its rotational axis is inclined at 98 degrees relative to its orbital plane, meaning it essentially rolls around the Sun on its side. During Voyager 2's approach, Uranus's south pole was pointed almost directly toward the Sun, giving the entire planet an unusual and baffling appearance in the spacecraft's cameras. The encounter revealed 10 previously unknown moons and a system of rings quite different from Saturn's. Then, Voyager 2 used Uranus's gravity to continue outward to Neptune. Neptune, the outermost major planet. The most distant world we have so far visited up close. The images returned were breathtaking. A vivid blue world with violent storm systems, including the Great Dark Spot, a storm comparable in size to Earth that had already vanished by the time the Hubble Space Telescope was turned toward Neptune a few years later. The moon Triton orbited Neptune in a retrograde direction, meaning it orbited in the opposite direction to Neptune's rotation. This strongly suggests Triton was a captured Kuiper Belt object rather than something that formed in place around Neptune. Triton's surface showed evidence of geysers of nitrogen gas erupting through its icy crust, driven by heating from sunlight absorbed beneath the surface. The images of Triton remain, decades later, among the most alien and beautiful ever returned by a spacecraft. The whole encounter lasted a few days in August 1989. Then Voyager 2 swept past Neptune, used its gravity for a final push, and continued outward. After Neptune, there was nothing left to visit. The spacecraft was already moving faster than the Sun's escape velocity. It had no way to stop. No way to turn back. It was committed to the void. The spacecraft carries a suite of scientific instruments designed to study planetary environments up close. Most of those instruments have now been shut down, either because they're no longer functioning or because there's not enough power to run them. The plasma wave subsystem still returns data about the electric and magnetic waves in the interstellar medium. The cosmic ray subsystem still detects and counts high-energy particles from outside the solar system. The magnetometer still measures the local magnetic field. The low-energy charged particle instrument remains operational. These instruments have been quietly recording the environment around the spacecraft as it moves through interstellar space, sending that information home at the speed of light. At its current distance, that signal takes about 19 hours to arrive after traveling at the fastest possible speed. A signal leaves the spacecraft, crosses more than 12 billion miles of space, and arrives at the Deep Space Network antennas on Earth after nearly a full day of travel. Then it's processed, analyzed, and added to a database of scientific knowledge about the environment between the stars. Nobody has ever had this kind of data before. The region beyond the heliopause was completely unexplored until Voyager 1 crossed it in 2012. Voyager 2 crossed the heliopause in November 2018. The heliopause is the boundary where the solar wind, the constant stream of charged particles flowing outward from the Sun, finally loses the battle against the pressure of the interstellar medium. Inside the heliopause, you're in the sun's territory. The solar wind sweeps outward in all directions at hundreds of miles per second, carving out a bubble in the interstellar medium called the heliosphere. The shape of this bubble is not a perfect sphere. The sun's motion through the interstellar medium compresses the heliosphere on the leading side and stretches it into a tail on the trailing side. At the heliopause, the pressure of the solar wind equals the pressure of the interstellar medium pushing back. It's a dynamic balance, shifting slightly as the sun's activity changes over its 11-year solar cycle. Beyond the heliopause, the sun's wind has been stopped. The interstellar medium takes over. You're in the space between the stars. When Voyager 2 crossed that boundary, it entered true interstellar space, and scientists immediately noticed something interesting. The particle environment changed, suddenly and dramatically, exactly as predicted. Inside the heliosphere, the dominant particles were those coming from the sun. Outside, the dominant particles were cosmic rays originating from distant stellar events. The spacecraft had crossed into a genuinely different physical environment. And it's still in that environment today, moving through the interstellar medium at about 34,000 miles per hour relative to the sun, roughly 9.5 miles per second, every second of every day. Right now, as you're watching this, Voyager 2 is moving outward through the Milky Way. That number, 34,000 miles per hour, sounds significant until you understand the scales involved. The solar system, including the distant Oort cloud of comets that surrounds it at its outermost edge, extends roughly 1 to 2 light-years from the sun. Even at 34,000 miles per hour, it will take Voyager 2 approximately 30,000 years just to exit the solar system's outer boundary in any meaningful structural sense. The nearest star to our Sun, Proxima Centauri, sits 4.24 light-years away. At current speed, Voyager 2 would take something in the range of 76,000 years to cover that distance. But it isn't headed toward Proxima Centauri. It's moving in the direction of the constellation Telescopium in the southern sky. In approximately 40,000 years, it will pass within about 1.7 light-years of the red dwarf star Ross 248. Not a dramatic close encounter, just a passing proximity in the enormous emptiness between stars. After that, in about 296,000 years, it will pass within about 3.3 light-years of Sirius. Sirius is the brightest star in our night sky, a brilliant white star nearly twice as massive as the Sun, burning about 25 times more luminously. 3.3 light-years is still an enormous distance, roughly the same as the current distance from the Sun to the nearest stars. From Voyager 2's hypothetical vantage point during this closest approach, Sirius would be the nearest star in the sky, brighter than anything around it, but still just a point of light, not a disk, not something you could resolve with the naked eye. After that passage, Voyager 2 continues into the broader galaxy, into the future. No destination, no plan, just momentum. To really grasp what 10 trillion years means for Voyager 2, you first need to understand what 10 trillion years means for the universe. The universe is currently about 13.8 billion years old. 10 trillion years is roughly 725 times the current age of the universe. This ratio is genuinely difficult to hold in the mind. The age of the universe, already staggering in its own right, is compressed into less than 1% of the time frame we're discussing. Everything that has happened in cosmic history, from the Big Bang to this moment, the formation of the first stars, the assembly of galaxies, the birth and death of billions of stellar generations, the formation of Earth, the entire history of life, all of it is a small fraction of the time span Voyager 2 will traverse. During the time the spacecraft drifts through the cosmos, over that span, the universe itself will pass through phases of existence that most people have never considered. Phases that are understood by physicists and cosmologists, but rarely discussed in popular accounts. Phases that will make the universe we currently inhabit look like a brief, bright, and exceptional moment in an otherwise cold and quiet history. The era we live in right now is called the Stelliferous Era. It's the age of stars. The period when galaxies blaze with fusion-powered light, when new stars are continuously born from collapsing clouds of gas and dust, when the night sky, from any vantage point in any galaxy, is rich with photons produced by nuclear fusion in stellar cores. This era started a few 100 million years after the Big Bang, when the first stars ignited, and it's still going today. But it won't last forever. The Stelliferous Era is itself temporary, and understanding its end is essential to understanding where Voyager 2 ends up. Stars are not eternal. Every star is running on a finite supply of fuel. Hydrogen, the most abundant element in the universe. Stars shine because they fuse hydrogen atoms into helium, releasing energy in the process. The relationship that governs this is E equals mc squared. Mass is converted to energy. A small amount of mass produces an enormous amount of energy because the speed of light is so large. In the core of our Sun, about 600 million tons of hydrogen are converted to helium every second. 4 million tons of that hydrogen are converted directly to energy, radiated outward as light and heat. This is why the Sun shines, and why it cannot shine forever. The most massive stars, those 10 or more times the mass of the Sun, burn through their hydrogen in just a few million years. They live brilliantly and die violently, collapsing and exploding as supernovae, sometimes leaving behind neutron stars, sometimes collapsing further into black holes. Medium-sized stars, like our Sun, last around 10 billion years before they swell into red giants, shed their outer layers as planetary nebulae, and leave behind slowly cooling white dwarfs. But the smallest stars, the red dwarfs that make up somewhere around 70 to 80% of all stars in the Milky Way by number, are extraordinarily long-lived. Red dwarf stars are small, cool, and extremely dim. They burn their hydrogen slowly and carefully. They maintain a state of equilibrium at surface temperatures far lower than our Sun's, somewhere between 3100 and 6700 degrees Fahrenheit, compared to the Sun's roughly 10,000 degrees Fahrenheit. They're also convective throughout their entire volumes. This is different from the Sun, where convection only occurs in an outer shell. In a fully convective star, the entire volume of hydrogen is continuously circulated through the core where fusion occurs. This means red dwarfs can burn essentially all of their hydrogen, not just the portion in their cores. They're extraordinarily efficient. Some red dwarfs will burn for trillions of years. The very least massive ones, those close to the theoretical minimum mass needed to sustain hydrogen fusion, about 8% of the Sun's mass, have theoretical main sequence lifetimes of roughly 10 trillion years. So as Voyager 2 drifts through the galaxy over the coming eons, the stellar landscape around it will change beyond recognition. The massive, brilliant blue stars that dominate our current sky in terms of visual impact will be long gone within the first few 100 million years. Stars like our Sun will finish their lives within the next 5 to 6 billion years. Even many red dwarfs that were born when the galaxy was young will have burned out within the next trillion years or so. What remains as the eons compound, approaching 10 trillion years, is a galaxy slowly dominated by only the very smallest, dimmest, most frugal stars. And their numbers will be dwindling. The night sky, from any hypothetical vantage point near Voyager 2, will grow darker. Not quickly, not noticeably on any human timescale, but steadily, irreversibly, over timescales that make the current age of the universe look like a fleeting moment. The spacecraft's power source is already failing. Voyager 2 runs on radioisotope thermoelectric generators, a technology that converts the heat of radioactive decay directly into electricity. No moving parts, no combustion, no solar panels needed. Just the steady, predictable decay of radioactive atoms releasing energy that can be captured and used. The fuel is plutonium-238, an isotope chosen specifically for its half-life and the nature of its decay products. Plutonium-238 decays by releasing an alpha particle, a helium nucleus, and transforming into uranium-234. This decay releases heat. The heat is converted to electricity through thermoelectric devices, materials that generate a voltage when there's a temperature difference across them. The design is elegant in its simplicity. No complex machinery, no fuel pumps or combustion chambers, just physics. Plutonium-238 has a half-life of about 87.7 years. Every 87.7 years, the amount of plutonium in the generator drops by half, and the power output drops by half. When Voyager 2 launched in 1977, its generators were producing about 470 watts, enough to power a small space heater. By 2026, that figure had dropped to roughly 50 watts or less, enough to run a few incandescent light bulbs. The science team on Earth has had to make increasingly difficult choices about which instruments to keep running. Heaters that prevent components from freezing have been switched off. Redundant backup systems have been permanently disabled. Every remaining watt of power has been accounted for and allocated to the highest priority science. At some point in the next several years, the power will drop too low to run any instruments at all, and then below the threshold needed to communicate at all. The last signal will leave the spacecraft, travel for more than a day across the void, arrive at the Deep Space Network's massive dish antennas, and then there will be nothing more. Silence. For the first time in its existence, Voyager 2 will be completely alone. No contact with Earth. No instructions. No acknowledgement that it exists. Just the spacecraft, moving through interstellar space, carrying everything that was placed on it in 1977. The silence won't slow it down. This is one of the most important things to understand about Voyager 2's future. In the vacuum of space, with no friction acting on it, the spacecraft will maintain its velocity indefinitely. There's no air resistance, no drag, nothing pushing against its motion. Newton's first law operates perfectly in space. An object in motion remains in motion unless acted upon by an external force. The only external force that will act on Voyager 2, other than the trivially small pressure of the few interstellar particles it sweeps through, is gravity. And gravity, over the next 10 trillion years, will indeed play a profound and complicated role. As the spacecraft drifts through the interstellar medium, it will occasionally pass close enough to individual stars that their gravitational pull noticeably bends its trajectory. Not every stellar encounter matters equally. A star 100 light-years away has negligible effect. A star a light-year away has a small but real effect. A star a tenth of a light-year away has a significant effect. A close encounter within a few astronomical units with a compact, massive object could be dramatic. Each close stellar encounter adjusts the spacecraft's velocity and direction by some amount, sometimes by a tiny fraction of a degree. Occasionally, if the approach is particularly close to a particularly massive object, by a significant angle. Over millions and billions of years, these small adjustments accumulate. The path of Voyager 2 is not a straight line through eternity. It's a slow, wandering curve, shaped continuously by the gravitational landscape of the galaxy around it. The spacecraft is, in effect, doing a gravitational random walk through the Milky Way, responding precisely and deterministically to the gravity of every object it passes near. But the accumulated result of millions of such encounters over trillions of years produces a path that is in practical terms completely unpredictable. The galactic merger is the most dramatic single event in Voyager 2's 10 trillion-year future. The Milky Way and the Andromeda Galaxy are approaching each other. They're currently about 2.5 million light-years apart. They are moving toward each other at roughly 68 miles per second, driven by their mutual gravitational attraction. The collision is inevitable. In approximately 4.5 billion years, the two galaxies will begin their first close approach. The word collision is somewhat misleading. When galaxies merge, stars rarely collide directly. The distances between stars within a galaxy are so enormous that even when two galaxies interpenetrate each other, the probability of any individual pair of stars coming close enough to physically interact is very small. What happens instead is a gravitational restructuring. The two galaxies pass through each other, their shapes violently distorted by tidal forces. Long streamers of stars are pulled out into space, forming structures astronomers call tidal tails and tidal bridges. These can extend for hundreds of thousands of light-years. The spiral arms of both galaxies are disrupted and flung outward. Stars that were on orderly circular orbits around the galactic center find themselves on highly elliptical or even hyperbolic orbits. The gas clouds within both galaxies are compressed as they collide and interact with each other, triggering enormous bursts of new star formation. Starburst galaxies. Galaxies forming stars at rates many times higher than normal result from exactly this kind of merger. For a time, the merged system blazes brighter than either of its progenitors. A last magnificent flare of stellar birth before the era of new star formation begins to wind down permanently. Then the two galaxies gravitationally pull apart somewhat, orbit around each other, and swing back together for a second approach. And a third. Each pass merges them more completely, mixing the two stellar populations, redistributing stars throughout a larger volume. Eventually, over perhaps 2 to 3 billion years after first contact, the two galaxies settle into a single merged structure. Computer simulations of this merger consistently predict the result will be an elliptical or lenticular galaxy, lacking the graceful spiral arms that both the Milky Way and Andromeda currently display. The name sometimes given to this predicted merged galaxy is Milkomeda. During this merger, Voyager 2 will be along for the entire process. Its path through space will be altered enormously by the gravitational upheaval as the combined hundreds of billions of stars from the Milky Way and the hundreds of billions of stars from Andromeda mix reorganize. Stars from Andromeda that were previously more than 2 million light-years away will become part of the same gravitational system. The gravitational terrain the spacecraft navigates will become far more complex and dynamic than anything it has experienced in the few billion years before the merger. New, close stellar encounters will occur that would never have happened if the galaxies had remained separate. The spacecraft's gravitational wander will be perturbed by the chaos. But the spacecraft itself survives the merger. It's just a small metal object moving through space. The probability that it happens to be in the direct path of another star during the merger process is vanishingly small. It simply continues. Its course, altered by the gravitational upheaval, but physically undamaged. At the center of the Milky Way sits Sagittarius A, a supermassive black hole with a mass of about 4 million times that of our Sun. At the center of Andromeda sits a different, supermassive black hole. Its mass is estimated at somewhere between 100 million and perhaps 200 million solar masses. The Andromeda central black hole is dramatically more massive than our own. When the two galaxies merge, these two supermassive black holes will eventually find themselves within the same merged galaxy. Their mutual gravitational attraction will begin pulling them toward each other. But this process is extraordinarily slow. Two supermassive black holes in a recently merged galaxy don't simply rush together. First, they sink toward the center of the merged system through a process called dynamical friction. Stars near each black hole are gravitationally deflected as the black hole moves through the stellar population. These deflected stars absorb some of the black hole's kinetic energy, slowing it down. The black hole loses energy and spirals gradually inward toward the center of the merged galaxy. Meanwhile, the other black hole is doing the same thing. Over hundreds of millions to billions of years, they approach each other. Eventually, they form a binary system, two supermassive black holes orbiting each other at decreasing separations. As they orbit, they emit gravitational waves. Ripples in space-time, predicted by general relativity and confirmed through observations of merging stellar mass black holes by the LIGO detectors. These gravitational waves carry away energy and angular momentum, causing the binary's orbit to shrink. The two black holes spiral ever closer together. And finally, in an event releasing an enormous amount of energy in gravitational waves, the two supermassive black holes merge into a single object. The resulting black hole will be extraordinarily massive. The combined mass of both, with some additional mass absorbed from stars consumed during the merger process. It will sit at the center of the merged Milkomeda galaxy. Voyager 2, drifting somewhere in the outer regions of the merged galaxy, is entirely unaffected by this event in any direct physical sense. Gravitational waves from the merger will spread outward from the galactic center at the speed of light. But by the time they reach the spacecraft, their amplitude will be negligibly small. The spacecraft doesn't notice. It continues its slow gravitational wander, its path indifferent to the titanic event at the galactic core. A few billion years into Voyager 2's journey, our own sun will be finished. The star that created the conditions for life on Earth, that powers our civilization, that has been burning for 4.6 billion years already, will exhaust its core hydrogen fuel. When a star like the Sun runs out of hydrogen in its core, nuclear reactions don't simply stop. Instead, the core contracts and heats up. The surrounding shell of hydrogen begins to fuse. The increased energy output causes the outer layers of the star to expand dramatically. The star swells into a red giant. Our Sun is expected to expand to perhaps 100 times its current diameter during its red giant phase. Depending on the exact details, it may or may not physically engulf Earth. But it doesn't matter whether Earth is literally swallowed. Long before the Sun reaches its maximum red giant size, Earth's surface will have become uninhabitable. As the Sun brightens during its approach to the red giant phase, even before it starts dramatically expanding, Earth's oceans will begin to evaporate. The water vapor enters the atmosphere, creating a greenhouse effect that accelerates warming. Eventually, the oceans boil away entirely. The surface temperature rises to hundreds of degrees. Life, as we know it, ends. This process begins, depending on various models, roughly 1 to 2 billion years from now. Not in the red giant phase. In the slow brightening of the main sequence Sun. After the red giant phase, the Sun will shed its outer layers in a series of pulses. This process creates an expanding shell of ionized gas, lit up by the ultraviolet radiation from the hot stellar core, called a planetary nebula. From a distance, it would be beautiful. A glowing sphere of gas, expanding outward, lit from within by the remnant of a star. What remains at the center will be a white dwarf, a dense stellar remnant roughly the size of Earth, but containing about half the Sun's original mass, composed mostly of carbon and oxygen, no longer producing energy through fusion, just slowly, patiently, radiating away its accumulated heat into the cold of space. Over billions of years, it will cool from white to yellow to orange to red to infrared and beyond. The theoretical endpoint of this cooling process is called a black dwarf, an object at essentially the temperature of the ambient universe. Cold, dark, still there, just no longer shining. The universe is not old enough for any black dwarfs to exist yet. The first white dwarfs to form, the remnants of the universe's first generation of stars, are still warm. They will cool to black dwarfs far in the future, long after the 10 trillion years we're contemplating. There's something about Voyager 2's situation at this point in its journey, several billion years from now, that deserves direct acknowledgement. The spacecraft was built by a civilization on a planet orbiting a star that will be cold and dark. Every person who designed Voyager 2, every engineer who built it, every scientist who planned its trajectory, every person who has worked on the mission since launch, every person who is alive on Earth today. All of us will have been gone for billions of years. The institutions that funded Voyager 2, NASA, the government of the United States, the broader structure of civilization that made it possible, will be gone. The languages in which we think and communicate will be gone or transformed beyond recognition. The culture, the science, the art, the history, everything we consider meaningful and valuable about human civilization at this moment in 2026 will be so ancient that no record of it may survive anywhere. And yet, Voyager 2 will still be there, still moving, carrying the sounds of a planet that no longer exists in any form we would recognize, carrying the golden record with its greetings in 55 languages, none of which are spoken anywhere in the universe. A message in a bottle thrown into an ocean that has itself changed beyond recognition since the bottle was thrown. The spacecraft will have outlasted not just us, but the very context in which it was created. And it will still be moving, 34,000 miles per hour, in a direction determined by a trajectory planned in the 1970s, adjusted by the gravity of every star it has passed since then. Going in the direction physics sends it, without purpose in the human sense, but not without meaning. The golden record deserves extended attention, because it represents the most explicitly human thing about Voyager 2. The record was conceived and designed by a team that included Carl Sagan, Ann Druyan, Timothy Ferris, John Lomberg, and others working in the mid-1970s. The team had a mandate that was both simple and overwhelming. Put something on the spacecraft that represents Earth, in case anyone ever finds it. They were given weeks to work. The result was a 12-inch gold-plated copper phonograph record, accompanied by a cartridge, a stylus, and detailed instructions for playing it, encoded in a way that requires only knowledge of physics and mathematics. The record contains 115 images, encoded in analog form in the audio signal. These images include photographs of Earth from space, mathematical diagrams, the structure of DNA, human anatomy, people from different cultures, cities, forests, oceans. They include a picture of a human hand touching a hand, a symbolic gesture of greeting or recognition. They include a diagram showing the hyperfine transition of hydrogen, the most common process in the most abundant atom in the universe, providing a fundamental unit of measurement. They include a map of the solar system's position relative to 14 pulsars. Pulsars are rotating neutron stars that emit regular pulses of radio waves, like cosmic lighthouses. Each pulsar has a unique rotational frequency. The map uses these frequencies as a coordinate system, identifying our location in the galaxy to anyone who can recognize the same pulsars we can. The record also contains sounds. The sounds of nature on Earth. Thunder, wind, rain, surf breaking on a shore, a volcano, an earthquake, the calls of birds, including the song of a white-throated sparrow, the sounds of insects, the songs of whales, haunting and complex, the laughter of a child, a mother's first words to her newborn child, and then music, a selection representing human musical culture that spans thousands of years and dozens of traditions. Bach's Brandenburg Concerto, No. 2, in F major, the first movement. Mozart's Queen of the Night aria from the Magic Flute. Music from Azerbaijan, Bulgaria, Senegal, Peru, China, India, Japan. Stravinsky's Rite of Spring. Louis Armstrong performing Melancholy Blues. Chuck Berry's Johnny B. Good. A Navajo night chant. An Australian Aboriginal song. The record is an attempt to say, we were here. We had music. We had language. We had cultures. We reached out into the universe because we were curious about it, and we wanted anyone out there to know that. It is, perhaps, the most optimistic object ever created by human beings. And it's on Voyager 2, moving through the interstellar medium. Right now. As the spacecraft drifts through the interstellar medium in the first billion years of its journey, what does it actually encounter? The interstellar medium is not empty, but it's extraordinarily sparse. The average density of matter in the interstellar medium of the Milky Way's disk is roughly 1 atom per cubic centimeter. By laboratory standards, this is a better vacuum than anything humans can currently create. But it's not nothing. There is matter out there. And over enormous timescales, even that thin scattering of particles matters. The interstellar medium is composed mostly of hydrogen, with significant helium and trace amounts of heavier elements. Most of the hydrogen is in atomic form, individual hydrogen atoms moving at low velocities. Some is in molecular form, pairs of hydrogen atoms bonded together. And some is in ionized form, individual protons stripped of their electrons by radiation from hot stars. The medium also contains dust grains. These are microscopic particles, mostly composed of silicates and carbon compounds, ranging in size from a few nanometers to perhaps a micron. They are the building material of planets, existing in dispersed form throughout interstellar space. And the medium is threaded through with cosmic rays. High-energy particles, mostly protons but also heavier nuclei, accelerated to nearly the speed of light by supernovae shockwaves, pulsar winds, and other energetic events. These cosmic rays move through interstellar space at speeds close to the speed of light. They can penetrate through materials. They can damage electronics. They can disrupt crystal structures in metals and semiconductors. Moving through this environment at 34,000 miles per hour, Voyager 2 sweeps through a thin but real stream of particles, dust, and radiation. The impacts of individual particles are trivially small. But over 1 billion years, these impacts accumulate. Surfaces are slowly eroded. Materials are slowly damaged. The spacecraft's physical state slowly degrades. The radioisotope thermoelectric generators will have fallen silent within the next decade or two. After that, the spacecraft has no power source, but it has thermal inertia. Objects in space don't instantly reach the temperature of their surroundings. They exchange heat through radiation, and that exchange takes time. In the deep cold of interstellar space, Voyager 2 will slowly cool toward the temperature of the cosmic microwave background. That temperature today is about minus 455 degrees Fahrenheit, or minus 270 degrees Celsius. It's extraordinarily cold. Cold in a way that makes the coldest temperatures on Earth seem balmy. At these temperatures, metals become brittle. Thermal vibrations in the crystal lattice, which keep metals somewhat flexible at room temperature, drop to nearly nothing. The components of Voyager 2 were not designed for sustained exposure to temperatures this extreme. The spacecraft was designed for deep space operation, and it's been remarkably durable. But over millions and billions of years, extreme cold, combined with radiation damage, will alter the physical properties of every material on board. Polymers and plastics will have become completely brittle and may have crumbled away. Rubber components will have failed. Adhesives will have lost their bonding properties. What remains at 1 billion years is mostly the metal structure. Aluminum, titanium, steel, gold. These metals are durable. They don't combust. They don't dissolve. They don't evaporate at any temperature found in interstellar space. But they do accumulate radiation damage. And they are, very slowly, hit by micrometeorites. The question of where Voyager 2 will be at 10 trillion years comes down to a question about the mathematics of chaotic systems. Not chaos in the colloquial sense. Chaos in the technical sense of dynamical systems theory. A system is chaotic if small differences in initial conditions lead to exponentially diverging outcomes over time. The classic example is the weather. Weather on Earth is chaotic. Small atmospheric disturbances, too small to measure or predict, grow into large differences in weather outcomes over days and weeks. This is why weather forecasting beyond about 2 weeks is extremely difficult, and beyond a month is essentially impossible. The trajectory of Voyager 2 over 10 trillion years is chaotic in exactly this sense. At each close stellar encounter, the spacecraft's velocity and direction are changed by some precise amount determined by the laws of gravity and the specific geometry of the encounter. But the outcome of each encounter depends on the exact positions and velocities of the spacecraft and the star involved. Any uncertainty in those values, however small, propagates through subsequent encounters. A trajectory calculation that is off by 1 meter in its initial position might differ from the true trajectory by light years after 10 trillion years. And we have no way to know the positions and velocities of all the stars. Voyager 2 will encounter over 10 trillion years with the precision needed to eliminate this divergence. Even if we knew the positions of all stars in the Milky Way today with perfect accuracy, which we don't, those stars are themselves subject to chaotic gravitational interactions with each other. Their positions in 1 million years are uncertain. Their positions in 1 billion years are very uncertain. Their positions in 1 trillion years are essentially unknowable. The long-term trajectory of Voyager 2 is, in principle, unpredictable. What we can do instead is reason probabilistically. Given what we know about the structure of the Milky Way, the density of stars in different regions, the typical velocities of stellar encounters, the rate at which close encounters occur, we can make statistical statements about where the spacecraft is likely to be at any given time. The first and most important statistical statement is this: Voyager 2 will almost certainly remain gravitationally bound to the galactic system. The spacecraft is moving at about 9.5 miles per second relative to the Sun. The escape velocity from the Milky Way's gravitational well depends on location within the galaxy, but in our local region, it's roughly 300 to 400 miles per second. Voyager 2 is moving at a small fraction of that. Barring an extraordinary gravitational encounter, the spacecraft has nowhere near enough velocity to escape the galaxy. It is permanently bound to the Milky Way, and by extension, to the merged Milky system that will eventually form. The spacecraft will remain within the galactic system for the rest of its physical existence. Its wandering is contained to a galaxy. A large galaxy, after the merger, perhaps one of the larger elliptical galaxies in the local group. But still a finite volume, still gravitationally bound, still a structure within which the spacecraft is trapped by its own relative slowness. The second statistical insight concerns how widely the spacecraft will have spread through the galaxy over 10 trillion years. In 10 trillion years, traveling at 34,000 miles per hour, Voyager 2 covers a total distance of roughly 3 sextillion miles. The Milky Way is roughly 100,000 light-years across. A light-year is about 6 trillion miles. The galaxy's diameter in miles is therefore about 600,000 trillion miles. In a perfectly straight line, Voyager 2 would cross the galaxy's full diameter roughly 5,000 times in 10 trillion years. Of course, its path is not straight. Every gravitational encounter bends it. The spacecraft isn't crossing the galaxy in a single trajectory. It's doing a slow, complicated random walk within the galaxy's gravitational well. This random walk, over sufficient time, causes the spacecraft to explore a large volume of the galaxy. In statistics, a random walk in a confined space eventually samples the entire accessible volume. The spacecraft, over 10 trillion years, has more than enough time to explore essentially all of the volume of the merged Milky galaxy. Its position at any given moment, including at exactly 10 trillion years, is therefore statistically random within that volume. Some regions are more densely packed with stars and would be visited more frequently. The galactic disk, where stars are concentrated, would be traversed more often than the sparse halo. The central regions, with their higher stellar density, provide more gravitational encounters per unit volume. But the spacecraft could be anywhere within this broad structure. The inner core, the outer halo, a sparse intergalactic region near the merged galaxy's edge. The statistics tell us only the broad envelope of possibility. There is one specific scenario that changes Voyager 2's fate completely: ejection. At some point, over 10 trillion years, the spacecraft might pass close enough to a very massive, very compact object to receive a gravitational kick exceeding escape velocity. Neutron stars and stellar mass black holes are the most likely culprits. Neutron stars are extraordinarily dense. They contain 1 to 2 solar masses compressed into a sphere about 12 miles across. Their gravitational fields are intense enough to bend space-time significantly. A spacecraft passing within a few astronomical units of a neutron star would experience gravitational forces far stronger than anything encountered near a typical red dwarf. The slingshot effect from such an encounter could impart a velocity of hundreds of miles per second. If that velocity is directed favorably, it could exceed the local escape velocity and propel Voyager 2 out of the galaxy entirely. The probability of such an encounter happening is small, but not zero. Estimating it requires knowing the density of neutron stars and black holes in the galaxy, the probability of a close enough approach, and the probability that the orbital geometry results in a near escape velocity kick rather than just a deflection. A rough calculation suggests that over 10 trillion years, there is perhaps a few % chance that Voyager 2 experiences an encounter dramatic enough to change its fate from gravitationally bound wanderer to galactic escapee. A few % is not negligible. And if it happens, everything that follows is different. Ejected from the galaxy, the spacecraft would drift into intergalactic space. At first, it would still be within the local group. The local group extends a few million light-years in all directions. Voyager 2, even if ejected from Milky, would remain within the local group's gravitational influence unless the ejection velocity was truly enormous. Remaining within the local group means remaining bound to that gravitational system. Eventually, even from intergalactic space within the local group, the combined gravity of Milky and the other local group members would pull the spacecraft back. Or the spacecraft would continue to drift until it encountered another galaxy in the local group and was captured gravitationally by that galaxy's stars. Either way, the spacecraft remains within the local group. Only a truly extraordinary velocity could send it beyond the local group's gravitational boundary. And that would require an even rarer and more dramatic encounter than mere ejection from Milky. The universe at 10 trillion years is not the lifeless void people often imagine when they think about the far future. That lifeless void comes much later. At 10 trillion years, the universe is still in the stelliferous era, though approaching its end. The very least massive red dwarfs, those with masses around 8 to 10% of the Sun's mass, have theoretical lifetimes of roughly 10 trillion years. Some models suggest the most long-lived red dwarfs could burn for 12 to 14 trillion years. So at 10 trillion years, these most extreme of stellar survivors are still going. Barely. They are emitting deep red light, far redder than any star we see today with the naked eye. Their luminosity is a tiny fraction of the Sun's. They're dim beyond easy description, but they are still fusing hydrogen into helium, still converting mass to energy, still shining. The galaxy at this epoch is dominated by stellar remnants, cooling white dwarfs, slowly fading from white to yellow, to orange to red as they lose their accumulated thermal energy. Some of these white dwarfs may have undergone thermonuclear surface detonations called novae, or in extreme cases, type Ia supernovae, as they accreted material from binary companions. These events would have been brilliant, brief flashes in an otherwise dim sky, neutron stars, pulsars, whose pulses may have slowed and faded, remnants of the most massive stellar generations. Stellar mass black holes, invisible by definition, but present everywhere, their existence revealed only by their gravitational influence on anything passing nearby. And scattered among this graveyard of stellar remnants, the last few living stars. The extreme red dwarfs, burning with such frugal efficiency that they've outlasted every other stellar class by billions or trillions of years. Voyager 2, drifting through the galaxy at 10 trillion years, will be in this environment, passing through a galaxy that is mostly dark, occasionally drifting through the light cone of a dying red dwarf, more often traversing the vast dark spaces between stellar remnants. Cold, silent, moving. The physical state of Voyager 2 at 10 trillion years requires careful thinking. The spacecraft is made of materials that have been subjected to 10 trillion years of cosmic ray bombardment, micrometeorite impacts, extreme cold, and the slow passage of time. Cosmic rays are the most persistent form of radiation damage. High-energy protons and heavier nuclei continuously punch through the spacecraft's materials. Each impact creates a trail of ionization and displaced atoms. Crystal defects accumulate. In metals, these defects weaken the crystal lattice, making the material more brittle. In a billion years, the cumulative radiation dose from cosmic rays is enormous. In 10 trillion years, it's 10,000 times that. The metals of the spacecraft have been irradiated on a scale that makes any laboratory radiation test seem trivial. The crystal structures of the aluminum and titanium and steel components will have accumulated vast numbers of radiation-induced defects. The materials will be physically weakened. They will not have shattered because there's no force acting on them in any direction that would cause a catastrophic structural failure. But they are damaged. Deeply, profoundly damaged at the microstructural level. The electronics have been non-functional for trillions of years. The antenna dish is still present, but damaged. The instrument boom is still attached, but fragile. The fuel tanks, long since empty, are intact metal shells. The radioisotope thermoelectric generators are still there, long since cold. The plutonium-238 has essentially completely decayed, going through daughter products and eventually becoming stable lead. The warmth is long gone. The spacecraft is cold as the universe around it, fractions of a degree above absolute zero. The golden record, physically, is the most durable component of the spacecraft. Gold plating on a copper substrate with analog information encoded as spiral grooves. Gold is the most chemically inert metal in common use. In the near vacuum of interstellar space, there's almost nothing to react with. No oxygen, no moisture, no corrosive chemicals. The primary threats to the record are radiation damage and physical impacts. Over 1 billion years, gold resists radiation reasonably well. Over 10 trillion years, the cumulative radiation damage is significant. The gold plating may have developed microscopic radiation damage that has altered its crystalline structure. The grooves encoding the information may have been partially filled in by redeposition of sputtered material from micrometeorite impacts. The overall record structure is still present. There's still a disk. It still has a flat surface. Whether the information encoded in its grooves is still recoverable is genuinely uncertain. Some of it probably is. Some of it probably isn't. But the physical record exists. And it still carries with it, in some form, the intention that was encoded there in 1977. The intention to communicate. The decision to put something meaningful on a spacecraft heading out of the solar system. That decision was made. That act happened. In a universe governed by deterministic physical laws, the causal trace of that act extends forward through time. It cannot be erased. The record was created. It was placed on the spacecraft. It left Earth. Those facts are permanent. Even when the grooves are worn beyond reading. Even when the gold is damaged beyond recognition. The fact that it was made and sent remains true forever. There's something that proton decay reveals about matter at extreme timescales. Not at 10 trillion years, but further out. Proton decay has never been observed. Experiments at facilities like the Super Kamiokande detector in Japan, a vast underground tank of ultra-pure water surrounded by sensitive light detectors, have searched for spontaneous proton decay for decades without finding it. This has placed lower bounds on the proton's lifetime. If protons decay at all, their mean lifetime must be longer than about 10 to the 34 years. Many theoretical models beyond the Standard Model predict proton decay. Grand unified theories, which attempt to unify the strong, weak, and electromagnetic forces into a single framework, generally predict proton decay with lifetimes somewhere around 10 to the 32 to 10 to the 38 years. At 10 trillion years, which is 10 to the 13th years, we're more than 20 orders of magnitude below the proton decay threshold in most models. The protons in Voyager 2 are completely stable. Every atom is intact. The iron atoms are iron. The aluminum atoms are aluminum. The gold atoms are gold. The copper atoms are copper. The spacecraft is made of the same elements it was always made of. This means Voyager 2 at 10 trillion years is still a real, physical object, not a cloud of fragments, not scattered atoms, a spacecraft, battered beyond anything its designers imagined, cold beyond anything they could have measured, dark in every way, but physically present, still moving through space at the velocity physics has given it. What ultimately matters most about this thought experiment is not the specific physics. The physics is fascinating, and it's real, but it points at something more important. Voyager 2 was built by beings who knew they would never see it reach another star. The designers knew the spacecraft would take tens of thousands of years to reach even the nearest stellar neighbor, and that they'd be gone long before. They knew the communication would end within decades. They knew the power would fail within a human lifetime. And they launched it anyway. Not because it was practical. Not because they expected a return on the investment in any direct sense. But because reaching out, because extending human presence into the cosmos in any form was worth doing. The Voyager program represents something about human nature that deserves acknowledgement. We are the only species on Earth, as far as we know, that builds objects designed to outlast not just ourselves, but our entire civilization. The pyramids of Egypt were built to last. The monoliths of Stonehenge were built to last. But none of these were built to outlast the sun. None were designed to survive the death of the planet. Voyager 2 will. Not forever. Its atoms will persist, but its structure will eventually degrade. But for longer than any other human artifact, it will remain, moving through the galaxy. Long after every other thing we've ever built has crumbled. The next few years are a threshold. The last signals from Voyager 2 will stop. The spacecraft will go dark, in the communication sense. And from that moment on, it moves through the universe without any connection to the world that made it. For thousands of years, it will drift through the outer solar system and into the interstellar medium, in a universe where humans, or whoever comes after us, might occasionally turn telescopes in its direction and think about it. For millions of years, it will be far beyond any technology we can currently imagine reaching. For billions of years, the civilization that made it will be long gone. For trillions of years, the star that warmed the planet it came from will be cold. For 10 trillion years, it will wander through a dimming, ancient galaxy, carrying the sounds of a world no longer there, and still moving, still following the trajectory that physics assigned it, still carrying everything that was placed on it by people who understood they were doing something that would outlast them in ways they couldn't fully comprehend. The spacecraft is out there right now, moving at 34,000 miles per hour in the direction of Telescopium, carrying the sounds of thunder and birds and whales and children laughing, carrying the music of Bach and Armstrong and Chuck Berry, carrying greetings in 55 languages that are being spoken on Earth right now by people who have no idea that their language is riding a spacecraft through interstellar space, carrying a golden record that will exist long after every other record ever made has crumbled, carrying a stylus and a cartridge and instructions for playing it, encoded in a language that requires only physics and mathematics to understand, carrying a map to where we live, made of pulsars whose heartbeats don't change, carrying everything we thought to put there, and going through the interstellar medium, through the gravitational wonders of 10 trillion years, through the galactic merger, through the slow fading of the stars, through a universe that will be almost unrecognizable by the time 10 trillion years have elapsed. The interstellar medium has a structure that most people never consider. It's not uniform. The space between stars is not a featureless expanse of identical thinly spread gas. It has regions, distinct physical environments with different temperatures, densities, and compositions. The nearest region to our Sun, extending a few hundred light years in most directions, is called the local bubble. It's an enormous cavity in the interstellar medium roughly 300 light-years across, with a much lower density of gas than the surrounding regions. This cavity is thought to have been carved out by a series of supernova explosions over the past 10 to 20 million years. The expanding shock waves from those supernovae pushed the surrounding interstellar gas outward, creating a region of hot, thin gas surrounded by a shell of denser material. We live inside this local bubble. Our Sun has been inside it for roughly the past 10 million years. Voyager 2 is currently in the local bubble, moving outward through the hot, thin gas of this cavity. In tens of thousands of years, it will approach the boundary of the local bubble. The boundary is not a sharp wall, but a gradual transition zone where the hot, thin gas of the interior gives way to denser, cooler interstellar gas outside. When Voyager 2 crosses this boundary, it will enter a different physical environment. The particle density will be higher. The temperature of the ambient gas will be lower. The magnetic field configuration will change. The spacecraft won't notice any of this directly because its instruments will be long since dead. But the physical environment around it will be genuinely different. Beyond the local bubble, Voyager 2 will move through the general interstellar medium of the Milky Way's disk. This medium is also not uniform. It contains giant molecular clouds, dense regions where gas and dust have accumulated to densities high enough for molecules to form. These clouds are the birthplaces of new stars. If Voyager 2 passes through such a cloud millions of years from now, the impact rate of dust particles will increase significantly. The particle density inside a giant molecular cloud can be thousands of times higher than the surrounding interstellar medium. The resulting increase in surface erosion would be noticeable. Not catastrophic, but measurable. Over millions of years inside a dense cloud, the surface erosion could amount to micrometers of material. In the context of a spacecraft designed with millimeter-thick metal panels, that's a small but real effect. The spacecraft could also receive a gravitational nudge from the mass concentration of such a cloud. The gravitational field of a giant molecular cloud is significant. Masses ranging from a few hundred to millions of solar masses, concentrated in a region of 10 to 100 light-years. A spacecraft passing within a few light-years of such a cloud would have its trajectory slightly bent by the cloud's collective gravity. These effects are small individually. Over hundreds of millions of years, they accumulate. The heliosphere itself is a remarkable structure that Voyager 2 has now left permanently behind. Understanding it helps appreciate what the spacecraft has left behind and what it has entered. The heliosphere is the region of space dominated by the solar wind. It extends from the Sun outward in all directions until the solar wind's pressure equals the pressure of the interstellar medium pushing back. At this boundary, the heliopause, the solar wind, is stopped. Beyond the heliopause, the interstellar medium holds sway. But the boundary is not a simple sphere. Our Sun moves through the local interstellar medium at about 12 miles per second in the direction of the constellation Hercules. This motion creates a pressure imbalance. On the leading side, the heliosphere is compressed. On the trailing side, it's stretched into a long tail. The heliosphere is more like a comet shape than a sphere. A compressed bubble on the leading face, and a long extended tail, sometimes called the heliotail, stretching behind. The Voyager probes crossed the heliopause at different locations. Voyager 1 crossed it in 2012 on the leading side, at about 122 astronomical units from the Sun. Voyager 2 crossed it in 2018 at a slightly different location, at about 119 astronomical units. The measurements at both crossing points revealed that the heliopause is not smooth or uniform. It has irregularities, ripples, regions of varying pressure and magnetic field intensity. The interstellar medium itself is not uniform at this scale either. The two Voyager probes have given us 2-point measurements, two specific locations where we've measured conditions in the very local interstellar medium. Both probes are still returning data about this environment. For now. Very soon, they'll fall silent. And humanity's in situ measurement of the interstellar medium will end until another probe reaches that distance. The scientific legacy of the Voyager program extends far beyond the specific measurements it returned. It changed how we think about our solar system and its boundaries. Before Voyager, the heliosphere was a theoretical construct. Its basic properties were inferred from theoretical models and indirect observations. The Voyager probes turned it into something we have actually measured. Before Voyager, the outer planets were distant blurs, even in the best telescopes of the 1970s. Voyager turned them into real worlds with distinct personalities. Jupiter the Giant, with its storms and violent volcanic moons. Saturn the Ringed, with its complex and beautiful ring system. Uranus the Tilted, with its strange polar orientation and quiet, cold beauty. Neptune the Distant, with its brilliant blue color and unexpected atmospheric violence. Each of these worlds had been merely a dot before Voyager flew past. Afterwards, they were places. The images Voyager returned inspired generations of scientists, engineers, students, and ordinary people. The photographs of Eo's volcanic plumes. The image of Neptune's great dark spot. The thin crescent of Saturn with its rings backlit by the sun. These images entered the cultural vocabulary of an entire civilization. They changed what space meant to people who had never studied astronomy. And the pale blue dot photograph, taken at Carl Sagan's insistence when Voyager 1 was about 3.7 billion miles away, became one of the most famous images in human history. A photograph of Earth as a tiny, barely visible point of light, suspended in a beam of sunlight. Sagan's words about that photograph, written in 1994, remain some of the most remarkable ever written about our place in the cosmos. The perspective those words offered, and the image that inspired them, came from a spacecraft now drifting through interstellar space. A spacecraft that will outlast everything. The specific fate of Voyager 2's components at 10 trillion years is worth thinking through systematically. The antenna dish is made of aluminum, a parabolic dish about 12 feet across. It has been pointed toward Earth since launch. It still points in that direction. At 10 trillion years, the aluminum will have accumulated an enormous amount of radiation damage. The crystal lattice of the aluminum will have defects at a density that would make the material extremely brittle by any earthly standard. But there's no force trying to bend or break the dish. It floats in space, experiencing no significant structural loads. So despite the radiation damage, the dish is likely still present as a connected structure. Still a dish shape, still pointing in the direction it was aimed decades after launch. A direction that no longer corresponds to Earth's location, because Earth has moved significantly in its orbit around the Sun over trillions of years. But the dish shape itself, that parabolic curve of aluminum, may still be there. Scarred, pitted by micrometeorites. darkened by accumulated radiation damage. But present. The spacecraft bus, the main body of the spacecraft, containing most of the electronics and subsystems, is made of aluminum and titanium, stronger materials. Also, heavily radiation damaged by 10 trillion years. Also pitted by micrometeorite impacts. The electronics inside have been irrelevant for trillions of years. Printed circuit boards, whose transistors and resistors degraded long ago. Magnetic tape recorders that stopped functioning within the first century. Batteries that went dead within years. All of this is long gone in any functional sense. But the metal boxes and frames that contained them are still there. The instrument boom, a long rod extending from the main spacecraft bus carrying several of the scientific instruments, is also likely still attached. The boom is made of metal. It was designed to keep instruments far enough from the spacecraft body to reduce electrical interference from the spacecraft's own systems. It's still doing that function, in the same sense that a piece of metal extending from another piece of metal always does. The instruments at the end of the boom are present but dead. Their optical surfaces may have been degraded by radiation. Their mechanical components, though never moving in interstellar space, may have undergone radiation damage to their materials. But the basic structure is likely still intact. At 10 trillion years, Voyager 2 is a ghost of a spacecraft. Recognizable if you knew what to look for. Not a cloud of fragments. Not a pile of dust. A spacecraft, dark, cold, and silent, but physically present. The Sun, at 10 trillion years, deserves mention here. Not because the Sun matters to Voyager 2 at that point, which it doesn't, but because our Sun's fate represents the context from which Voyager 2 was launched. The Sun will have been through its entire main sequence lifetime, its red giant phase, and its white dwarf phase long before 10 trillion years elapse. In fact, the Sun's main sequence will end in roughly 5 billion years. The red giant phase lasts about 1 billion years. The planetary nebula phase is brief, perhaps tens of thousands of years. The white dwarf cooling phase then begins. White dwarfs cool on timescales of billions to trillions of years. The Sun's white dwarf remnant, after 10 trillion years, will have been cooling for something like 9.9 trillion years. Starting from an initial temperature of perhaps 100,000 degrees, it will have cooled dramatically. White dwarf cooling follows a specific curve determined by the thermal properties of the carbon, oxygen, interior, and the thin hydrogen and helium atmosphere above it. After 10 trillion years of cooling, the Sun's remnant will be at a temperature somewhere in the range of a few hundred degrees above absolute zero. In terms of color, it would be emitting light almost entirely in the far infrared, completely invisible to the human eye. Not glowing visibly in any sense we'd recognize. An object you could only detect with a sensitive infrared telescope or by measuring its gravitational effect on surrounding space. A cold, dark, dense object, about the size of Earth, containing roughly half the Sun's original mass. Drifting through the merged Milky galaxy, moving on its own gravitational random walk, just as Voyager 2 is doing, but separately. Both of them drifting through the same old galaxy. The star that sent the spacecraft, and the spacecraft it sent. Both survivors of an enormous span of time, both cold, both dark, both moving. The merged Milky galaxy, at 10 trillion years, will have its own structure, different from either of its progenitors. Spiral galaxies, like the Milky Way and Andromeda, get their shape from two main sources. The first is differential rotation. Different parts of the galaxy orbit at different speeds, and this differential shearing creates the trailing spiral pattern. The second is density waves. Regions of slightly higher density that rotate through the disk and trigger star formation as they pass. After a major merger, both of these mechanisms are disrupted. The merger mixes the two stellar populations together and puts stars on highly elliptical orbits. The result is typically an elliptical galaxy, where stars move on a range of elliptical orbits in many different directions rather than all rotating in the same plane. The merged Milkomeda galaxy will be roughly elliptical, no spiral arms. A diffuse, roughly spherical or ellipsoidal distribution of stars and stellar remnants. The massive dark matter halos of both galaxies will have merged as well, since dark matter follows the same gravitational dynamics. The merged dark matter halo will be more massive than either original halo and will provide the overall gravitational framework within which the stellar remnants orbit. By 10 trillion years, the merger will have been complete for billions of years. The galaxy will have settled into a stable configuration. Stars and stellar remnants on a broad range of orbital configurations, governed primarily by the overall gravitational potential of the merged system. Voyager 2, drifting through this structure, will be subject to this overall potential. Its gravitational random walk takes place within this merged, stable elliptical galaxy. Star formation within Milkomeda will have essentially stopped by 10 trillion years. As we discussed, new star formation requires cold, dense gas clouds. The merger between the Milky Way and Andromeda will have triggered a burst of star formation as the gas clouds of the two galaxies collide and compress. This burst will be spectacular while it lasts, but it will consume an enormous fraction of the remaining cold gas. What's left after the merger-triggered starburst, and after the ongoing slow consumption of gas by star formation over the preceding billions of years, is very little cold gas. The gas that remains is mostly hot, ionized gas in the galaxy's halo, not the cold, dense molecular gas needed for star formation. Star formation may continue at a very low rate for some time after the merger. Individual dense pockets of gas might form stars here and there. But the era of substantial ongoing star formation will be over. By 10 trillion years, essentially no new stars have formed in Milkomeda for billions of years. The stellar population is entirely composed of objects formed before and during the early post-merger epoch. Long-lived red dwarfs from the original stellar populations of both galaxies. They're white dwarf remnants, neutron stars, black holes. The galaxy is old. Its stellar population is ancient. It is coasting on the energy of stars formed billions of years in the past. The dark matter content of the galaxy at 10 trillion years is essentially unchanged from today. Dark matter doesn't decay. It doesn't lose energy through radiation. It doesn't interact with ordinary matter or radiation in any way except through gravity. Dark matter particles, whatever they are, will still be present in the halo of Milkomeda at 10 trillion years, just as they were present in the halos of both galaxies when the merger began. The dark matter halo may have evolved somewhat. Dark matter particles can still scatter off each other through gravitational interactions, slowly redistributing. And the dark matter halos of both galaxies will have mixed together during the merger. But the total dark matter mass is conserved. It still provides the overall gravitational scaffolding within which Milky-Meda's stars and stellar remnants orbit. Voyager 2's gravitational random walk happens within this dark matter halo. The dark matter influences the spacecraft's trajectory through its gravitational effect on the orbital velocities of the stars the spacecraft encounters. The dark matter isn't directly detectable by Voyager 2 or by any instrument we currently have, but it's there, shaping the galaxy, governing the overall structure of the gravitational potential, making the merged Milky-Meda galaxy slightly more massive and slightly more tightly bound than its visible stellar content alone would suggest. The cosmic expansion of the universe is a factor that operates on much larger scales than the galaxy. The universe is expanding, not expanding into anything in particular, but expanding in the sense that the metric of space-time is stretching. Distant galaxies are moving apart from each other, not because they're moving through space, but because the space between them is growing. The expansion is driven by dark energy, a component of the universe with negative pressure that causes the expansion to accelerate. This acceleration has important implications for the long-term future of the universe. Objects that are not gravitationally bound to each other will be carried apart by the expansion, accelerating away until they eventually cross beyond each other's observable horizons. But objects that are gravitationally bound to each other, like the stars within a galaxy, or the galaxies within a cluster, or the clusters within a supercluster, are not pulled apart by the expansion. Their mutual gravity is stronger than the expansion's tendency to carry them apart. The local group, the galaxy group containing the Milky Way, Andromeda, and dozens of smaller galaxies, is gravitationally bound. It will not be torn apart by cosmic expansion. The local group will remain as a gravitationally bound structure, eventually merging into a single large object for essentially as long as any of its member galaxies exist. Beyond the local group, however, other galaxy groups and clusters are being carried away by the expansion. Already, the Virgo cluster, the nearest large galaxy cluster at about 50 million light-years, is receding from us. Other clusters are receding faster. In 1 trillion years, the universe beyond the local group will be essentially empty as seen from within Milky-Meda. All the distant galaxies will have been carried beyond the cosmological horizon. Their light will have been redshifted into near nothingness. The universe visible from Milky-Meda will shrink to the local group alone. Future astronomers within Milky-Meda, if any exist, will have no evidence that billions of other galaxies once existed beyond their own gravitational neighborhood. The evidence for the Big Bang, the cosmic microwave background, the large-scale structure of the universe will have faded away, washed out by expansion, redshifted beyond detectability. Voyager 2, drifting through Milky-Meda at 10 trillion years, will exist in a universe whose observable extent has shrunk dramatically compared to today. The trillions of galaxies visible in our night sky today will be gone, not destroyed, just beyond the horizon, carried away by an expanding universe that doesn't care about our desire to see it all. In thinking about 10 trillion years, there's a temptation to focus only on the physics and miss the human dimension of the story. The question of where Voyager 2 will be in 10 trillion years is, on one level, a physics question. On a deeper level, it's a question about what it means to send something into the universe that will outlast you. Outlast, not just you personally, but your species, your planet. your star, your galaxy as it currently exists. Voyager 2 was built in a specific historical moment, the 1970s, a decade of enormous tension and rapid change. The Cold War was ongoing. The space age had not yet peaked. The moon landings were recent memories. The environmental movement was gaining momentum. The personal computer hadn't been invented yet. The internet was a research project known only to a handful of specialists. The people who built Voyager 2 were working in this context. They were engineers and scientists of their time. They had access to the computing technology of the 1970s. They worked with knowledge of physics and astronomy as it stood in the mid-20th century. And they built something that will still exist when the sun is cold. The audacity of that achievement is easy to miss. We launch probes regularly now. The images from Mars rovers appear on our phones within minutes. Spacecraft orbiting Saturn or Jupiter send back data we analyze with modern computers. Space has become, in a certain way, familiar. The routine nature of current space missions makes it easy to forget that Voyager 2, specifically, is not routine. It is the only spacecraft ever built that will observe all 4 outer planets. It is one of only 2 human-made objects in interstellar space. It will be the last physical object built by human hands that exists in the universe after everything else we've built has crumbled. That's what makes Voyager 2 unlike anything else humanity has ever built. The program that sent Voyager 2 into space was conceived and executed by human beings who understood they were doing something that mattered beyond their own lifetimes. The Grand Tour mission concept was studied in the 1960s. The spacecraft were designed in the early 1970s, launched in 1977. The encounters with Jupiter, Saturn, Uranus, and Neptune happened between 1979 and 1989. And then the mission continued, evolving into the Voyager interstellar mission, dedicated to studying the boundary of the solar system and the interstellar medium beyond. The team that has operated Voyager 2 for nearly 50 years has changed generations. The original engineers and scientists are mostly gone. Younger people took over, who themselves are now aging. The mission continues. Data still arrives from about 12 billion miles away. Each day, a tiny trickle of information crosses the void from a spacecraft that was launched when Jimmy Carter was president, when the Berlin Wall was still standing, when the internet was a theoretical concept. There's something almost unbearably moving about this. The people who will be the last to hear from Voyager 2, the engineers and scientists who will be monitoring the Deep Space Network antennas when the final signal arrives, will be receiving a message sent by a spacecraft that has been traveling through interstellar space. They'll know it's the last one. And then it will stop, and Voyager 2 will continue its journey. Without them, without any of us, into 10 trillion years. The concept of escape velocity and why Voyager 2 cannot escape the galaxy deserves precise explanation. Escape velocity is the minimum speed needed to break free of a gravitational field without any further propulsion. On the surface of Earth, escape velocity is about 7 miles per second. Any object launched at that speed or faster, in any direction, will eventually escape Earth's gravity completely, without needing to burn any more fuel. Below that speed, no matter how fast you go, if you don't keep burning fuel, gravity will eventually pull you back. The galactic escape velocity, the speed needed to escape the Milky Way's gravitational field, depends on where you are in the galaxy. Near the Sun, in the middle of the galactic disk, it's roughly 340 to 345 miles per second. Voyager 2 is moving at about 9.5 miles per second. That's roughly 35 times slower than galactic escape velocity. For the spacecraft to escape the galaxy through its own momentum, it would need to be moving 35 times faster than it currently is. There's no way that happens without an external gravitational kick from a very close encounter with a very massive object. And as we've discussed, the probability of receiving such a kick over 10 trillion years is small but non-zero. This gravitational confinement is what makes Voyager 2 a permanent resident of whatever the Milky Way becomes. It cannot leave. It can wander. It can drift to the farthest edges of the galaxy. But the galaxy's gravity holds it. Like a coin dropped into a bowl. You can roll it in any direction, and it can reach any part of the bowl's surface. But it stays in the bowl. The galaxy is Voyager 2's bowl. And the bowl is not going anywhere. In the relevant cosmic sense, it will grow as it merges with Andromeda and eventually with other local group members. But it will remain a gravitationally bound structure, and Voyager 2 will remain within it. The orbital mechanics of how Voyager 2 came to have its current velocity is itself a story worth telling. The spacecraft left Earth at a velocity determined by the launch vehicle's power. It was inserted into an Earth escape trajectory. Then it coasted to Jupiter, taking advantage of gravitational assists from the planet's enormous mass. When Voyager 2 passed Jupiter, it was moving at a certain speed relative to the Sun. Jupiter, orbiting the Sun at about 8 miles per second, contributed some of its orbital momentum to the spacecraft. The spacecraft left the Jupiter encounter moving faster relative to the Sun than when it arrived. Not relative to Jupiter. In Jupiter's reference frame, the spacecraft came in with a certain speed and left with the same speed. But relative to the Sun, the spacecraft picked up speed equal to roughly twice Jupiter's velocity times the sine of half the deflection angle. The same thing happened at Saturn, and again at Uranus, and finally at Neptune. Each planet in turn boosted the spacecraft to a higher velocity relative to the Sun. The final velocity, after the Neptune encounter, was enough for Voyager 2 to exceed the Sun's escape velocity. It would have eventually anyway, since it was launched on an escape trajectory. But the gravity assists meant it could reach its final velocity with less fuel than a direct trajectory would have required. The trajectory planners at NASA's Jet Propulsion Laboratory optimized this sequence of gravity assists with the computing resources of the 1970s. They used hand calculations, slide rules, and early computers that occupied entire rooms. The precision of the trajectory that resulted, the ability to use 4 consecutive planetary gravity assists to send a spacecraft on a path through the outer solar system and into interstellar space, remains one of the great feats of applied orbital mechanics. And the momentum gained from those 4 planetary encounters is what Voyager 2 is still coasting on today. 49 years later, about 12 billion miles from Earth, still moving on the trajectory that was designed in the 1970s, still benefiting from the momentum borrowed from Jupiter and Saturn and Uranus and Neptune. The specific direction Voyager 2 is moving is worth specifying precisely. The spacecraft is moving in the direction of the constellation Telescopium in the southern sky. More precisely, it's heading toward a point in space at roughly 23 degrees south declination and 28 degrees east in galactic coordinates. This direction is roughly toward the galactic south, perpendicular to the galactic plane. This means Voyager 2 is moving out of the plane of the Milky Way's disk, angled downward relative to the disk in the conventional orientation. Moving out of the galactic plane has important implications for the density of stellar encounters the spacecraft will experience. The galactic disk, where most of the Milky Way's stars are concentrated, is roughly 1,000 light-years thick in our neighborhood. As Voyager 2 moves outward at its current angle, it will eventually rise above, or more accurately sink below, the densest part of the galactic disk. In the galactic halo, the sparse sphere of old stars and globular clusters surrounding the disk, stellar encounters are far less frequent. The stars are more widely spaced. The density of objects is much lower than in the disk. This means Voyager 2, once it has moved a sufficient distance from the disk, will experience fewer gravitational encounters per unit time than it would if it stayed within the disk. Its gravitational random walk will be slower to accumulate. The deflections of its trajectory will occur less frequently. In the halo, it might travel for millions of years without a significant stellar encounter, then pass close to a globular cluster where stars are densely packed and experience many encounters in a short period. The journey through the galaxy is not uniform. It has periods of relative quietude in the sparse halo and periods of more frequent interaction when passing through denser regions. What does the night sky look like from Voyager 2 right now? The spacecraft has no functioning cameras. Even if it did, it would need to transmit the images to Earth, which takes about 19 hours. But we can calculate what the sky looks like from its current position. The Sun, from Voyager 2's distance, appears as a bright star. Extremely bright compared to other stars, since it's so much closer, but a star nonetheless. Not a disk, not a visible sphere, a point of light. The brightest thing in the Voyager 2 sky. The other stars appear very much as they would from Earth, since the spacecraft is not far enough away to significantly alter their apparent positions relative to each other. The constellations look essentially the same from Voyager 2 as they do from Earth. The nearest stars would be very slightly brighter from Voyager 2's position than from Earth, since the spacecraft is about 1,000th of a light-year closer to them than Earth is. But this difference is imperceptible. To human eyes, looking at the sky from Voyager 2's location would be indistinguishable from looking at the sky from Earth. Same constellations. Same stars. Same apparent positions. Just with the Sun being a bright star in the direction of telescopium, rather than being the enormous blazing disk we experience on Earth. The sky from Voyager 2 is both alien and familiar. Alien, because the Sun has been reduced to a star. Familiar, because everything else looks the same. This is actually a profound observation about the distances involved. We're about 12 billion miles from Earth. 12 billion miles. A number that is genuinely difficult to comprehend. And yet the sky looks the same, because the nearest stars are so much farther away that even 12 billion miles is negligible in comparison. Space is astonishingly, almost insultingly, large. The gravitational influence that Voyager 2 has exerted on the solar system during its journey is not zero. It's small. Extraordinarily small. But not zero. Every mass in the universe exerts a gravitational influence on every other mass. The spacecraft has been exerting a tiny gravitational tug on everything it passes near. On the moons of Jupiter, during its flyby, on the rings of Saturn, on the icy moons of Uranus, on Triton and Neptune. On the comets and Kuiper belt objects, it has passed through the outer solar system. On the interstellar gas and dust particles, it has passed near. On the stars, it will pass near in the future. These influences are so tiny as to be completely immeasurable with any instrument we have or will likely ever have. The spacecraft weighs a little under 2,200 pounds. Jupiter weighs about 2 times 10 to the 27th kilograms. The gravitational effect of 2,200 pounds on Jupiter is essentially non-existent. But the laws of physics make it non-zero. And, in a deterministic universe, that tiny effect propagates forward. Every object that Voyager 2 has interacted with gravitationally is, in principle, in a slightly different position than it would have been if Voyager 2 had never existed. These differences are smaller than the quantum uncertainty in the positions of particles. They are undetectable. They are, for all practical purposes, nothing. But in the precise mathematical sense of physical law, they are real. Voyager 2 has been leaving its mark on the universe since the moment it was launched, and it will continue to do so for as long as it continues to exist. 10 trillion years of leaving barely perceptible gravitational fingerprints on every star it passes near. A legacy written in the language of gravity, far too faint to read, but real nonetheless. The temperature of deep interstellar space is determined by the cosmic microwave background radiation. This radiation fills the entire universe uniformly. It has a temperature of about -455 degrees Fahrenheit today. An object in deep interstellar space, far from any star, will equilibrate to this temperature over time. It will absorb photons from the cosmic microwave background and emit photons from its own thermal radiation until it reaches a steady-state temperature that matches the background. For a spacecraft like Voyager 2, this equilibration happens slowly. The spacecraft has significant thermal mass. It will take a long time to cool from its current operating temperature to the equilibrium temperature. But over millions of years, it will cool. Over tens of millions of years, it will be indistinguishable from the background temperature. As the universe expands and the cosmic microwave background cools further, the equilibrium temperature drops. The spacecraft cools along with it, asymptotically approaching, but never quite reaching, absolute zero. At 10 trillion years, the spacecraft is at an extraordinarily low temperature, fractions of a degree above absolute zero. At this temperature, thermal vibrations in the crystal lattice of the spacecraft's metal components are almost non-existent. The atoms are essentially motionless, except for the quantum mechanical zero-point motion that persists even at absolute zero. This is the world of quantum mechanics at its most extreme. Temperatures so low that quantum effects dominate. A metal structure at this temperature would be brittle in a way that has no earthly analogy. Not just cold. Fundamentally quantum mechanical in its behavior. The distinction between solid and amorphous, between crystal and glass, becomes blurred at these temperatures over extreme timescales. The spacecraft exists in a physical regime that no laboratory on Earth has ever approached for any extended period. There's something worth understanding about the power situation on board Voyager 2, because it illustrates a fundamental physical truth about energy and time. Radioisotope thermoelectric generators are not rechargeable. They have no off switch. They cannot be replenished. From the moment Voyager 2 was launched, the decay of the plutonium in those generators has been occurring continuously, second by second, year by year. Every atom of plutonium-238 that decays becomes an atom of uranium-234. Over the spacecraft's nearly 50-year history, the amount of plutonium has declined dramatically. The half-life means that after 87.7 years, half is gone. The spacecraft hasn't reached its first half-life yet, but it's close. And the power output has tracked that decay curve downward throughout the mission. There was never a moment when anyone could add more fuel. There was never a way to reset the clock. The power started at 470 watts on launch day in 1977, and it has gone down every single day since. This means the mission's science capabilities have been contracting throughout its entire existence. Every decade, instruments have been shut off. Every decade, capabilities have been sacrificed to keep the most important systems alive. The science team has had to make choices, again and again, about which data to collect and which to abandon. It's a kind of slow triage, conducted by engineers working with a spacecraft about 12 billion miles away, unable to visit it, unable to repair it, unable to do anything except send commands and listen to responses. And soon, the responses will stop. The power will drop below the threshold needed for communication. The antenna will still be pointed toward Earth. The radio transmitter will still technically be present. But it won't have enough power to produce a signal strong enough to be detected by the Deep Space Network antennas. And the spacecraft will fall silent. Not gone, still there. Still moving, but no longer speaking to us. The Deep Space Network is the infrastructure that makes communication with Voyager 2 possible. It consists of 3 large antenna complexes located in California, Spain, and Australia. They're spaced approximately 120 degrees apart in longitude, so that as Earth rotates, at least one of the complexes always has line of sight to any spacecraft in deep space. The antennas themselves are enormous. The largest dishes at each complex are 70 meters in diameter. 70 meters is about 230 feet across. The dish surface has to be shaped to a precision of a few millimeters across its entire diameter to focus the incoming radio waves onto the receiver at the focal point. The receiver at the focal point must be extraordinarily sensitive. The signal from Voyager 2, arriving from about 12 billion miles away, is incredibly faint. The power received from Voyager 2's transmitter, arriving at Earth after that enormous journey, is roughly 20 billion times less than the power of a modern smartphone's radio signal. It is among the faintest signals ever detected by human instruments. But the Deep Space Network can hear it. Barely, with careful signal processing. With receivers cooled to cryogenic temperatures to reduce thermal noise, with computer algorithms that average the incoming signal over time to pull it out of the background noise. But it works. The antennas hear Voyager 2. They will continue to hear it for a few more years. And then they won't. And that will be the last contact humanity has with the most distant thing humanity has ever built. In the context of Voyager 2's 10 trillion-year journey, the 50 years or so of communication represent almost nothing. 50 years out of 10 trillion years is 5 times 10 to the negative 12th. A number so small that if you tried to express it as a fraction of a second out of the age of the universe, it would be incomparably tiny. The period of active communication with Voyager 2, from launch to the last signal, is to 10 trillion years, as a single heartbeat is to all of recorded human history, multiplied by many thousands. And yet those 50 years are the only period during which the spacecraft has any connection to the civilization that built it. After the last signal, Voyager 2 is entirely alone, moving through a galaxy that doesn't know it exists, carrying information that no one is around to receive. The story of Voyager 2, in the context of its full 10 trillion year existence, is mostly a story of silence, of drifting, of being, of moving through a universe that is indifferent to the craft's existence. The 50 years of communication are a tiny parenthesis at the very beginning. A brief window during which a civilization briefly spoke to its most distant emissary. And then the window closes, and 10 trillion years of silence begin. What would it mean if something found Voyager 2? Not in 1,000 years. Not even in 1,000,000. But in 10 trillion years, or somewhere along that journey, the probability is low. But the thought is worth following. Any civilization capable of detecting and retrieving Voyager 2 would need to be extraordinarily technologically advanced. Finding a spacecraft-sized object in the vastness of interstellar space requires either extraordinary instruments or extraordinary luck. The spacecraft's radar cross-section is small. It doesn't emit radio waves after its transmitter stops. It doesn't emit visible light. It emits a tiny amount of thermal radiation from its metal surfaces at temperatures very close to absolute zero. Detecting this would require instruments of sensitivity we can barely conceive of. But let's say someone found it. They would have in their hands a gold-plated record, instructions for how to play it, a stylus and a cartridge. They would play it. If they could decode the analog images, they would see photographs of Earth, of human faces, of our solar system, of our DNA, of our mathematics. They would hear the sounds of thunder and birdsong. They would hear music, human music, music that was recorded by beings who have been gone for billions or trillions of years. The civilization that made the record, the planet it came from, the star that warmed that planet, all long gone. The record itself would be the only evidence they ever existed. An artifact, a message from a species to the unknown. Whether that message can still be decoded after 10 trillion years is uncertain. But the intention behind it, the deliberate choice to communicate, that is clear from the structure of the record itself. It was made by beings who hoped someone, somewhere, someday, might find it. And if they do, it will be the most remarkable discovery in their history. Proof that other beings existed in the universe. Proof that they reached out. Proof that they had music. That they had language. That they had children who laughed. That they listened to the songs of whales. That they looked up at the stars and sent something into them, hoping. The Voyager program costs, in inflation-adjusted terms, something like $1 billion or more in total. This seems large until you consider what it bought. The first detailed images of 4 outer planets. The discovery of active volcanism beyond Earth. The discovery of potential subsurface oceans. The first in-situ measurements of interstellar space. Data that fundamentally changed our understanding of the outer solar system. And the Golden Record, launched into space as a message from humanity. For the cost of a few hundred feet of urban real estate in a major city, or a fraction of a single large commercial aircraft, humanity purchased scientific knowledge that will inform space science for the rest of human history, and a spacecraft that will outlast human history itself. The economics of the Voyager program are, in this sense, extraordinary. The return on investment is not measurable in dollars. It's measurable in knowledge, in inspiration, in the changed understanding of our solar system and our place in it, and in the strange, quiet fact that somewhere out there, moving at 34,000 miles per hour through interstellar space, is a machine we built, carrying everything we thought to put on it. Still going. When you consider that context, the $1 billion seems almost absurdly cheap. What price is appropriate for sending a part of humanity to the stars? Even a small, metal, eventually silent part. Even a part that carries no humans, only their sounds and their mathematics and their music. Even a part that will drift for 10 trillion years through a universe that doesn't know it's there. The Voyager program's cost bought something that lasts longer than almost anything else we will ever do. That is not a bad return on investment. Not bad at all. The question we're asking, where will Voyager 2 be in 10 trillion years, is impossible to answer with precision. But the shape of the answer is clear. Somewhere within the merged Milky galaxy, or possibly beyond its boundaries, if a rare gravitational ejection event has occurred. Moving through a universe far older than we can currently comprehend. Through a galaxy populated mostly by stellar remnants. Under a sky that contains only the last few red dwarfs still burning, and the vast darkness between their faint, deep red points of light. Cold, dark, damaged, but physically present. Still moving, still carrying the golden record, still carrying the sounds of thunder and birdsong and ocean surf, still carrying the music of Bach and the blues, still carrying the greetings of 55 languages, still carrying a map made of pulsars pointing back to where it came from, pointing back to a location in the galaxy where, billions of years ago, a yellow star warmed a blue planet, and on that planet, beings arose who looked up at the sky and decided to send something out into it. The spacecraft is out there right now, moving every second, every hour, 34,000 miles per hour, in a direction determined by physics and by the choices of engineers who are mostly gone. It will still be moving in a century, in 1,000 years, in 1,000,000 years, in 1,000,000,000 years, in 10 trillion years. The universe will have aged beyond recognition. The stars we know will be memories encoded in no mind that exists. The sun will be cold. Earth will be whatever it becomes after being consumed or heated beyond life. And Voyager 2 will be there, out in the dark, still going. A small metal thing with a golden disc attached. The last legacy of a species that once stood on a planet under a yellow star and reached for the sky. Good night.